Hello members, you're welcome to today's session. We are going to look at analysis of variances specifically for those people who are going to do experimental research. We are going to collect data on different parameters, maybe gross parameters of plants, soil, physical, chemical, biological parameters, where you find that most of the data you collect is continuous data. So some of the things you must do are like checking normality of the data, talking about analysis of variance, mean comparison, hypothesis testing, and all that. So today that's what we are going to look at. So I supplied you with data last time. RCBD example contains different data sets within, both in long and wide formats. And R does more of the long format than the wider format. So we are going to be importing in the wider format, the long format. So let's start as usual by loading the data. So as you know, loading the data, I'll just click Excel. I load in, the data is already in my working directory, RCPD example. I just load it in. And I'm not just going to take this, like I told you, it is in this format. You can see this is a wider format. So I'm just going to pick this very one, this one here. You already have it there. It is in this format, and this is the one that can be easily interpreted by R. And I won't actually import, but I'm interested in getting this code and paste it here so that I can use it next time. And maybe I can do some simple editing there. Okay. So with that, I run, and run. So I'm able to view my data here. So this is the first viewing. It is a good practice to always save our data. So let's say the session 2. By this time, I'm doing ANOVA, analysis of variance. Analysis of variance, that's what I'm doing today. So before you do all this analysis or whatever, you need to first check for normality, because when we talk of analysis of variance, that is a parametric method. But we also have a non-parametric method, the equivalent of ANOVA, which is man-Whitney U-test. So under which circumstances do we use these two? Parametric methods like ANOVA, you only use it when the data is normally distributed. And that one, you do it by carrying out, by maybe plotting a histogram and then confirming with the Shapiro-Wilk test. If you find that the p-value is more than 0.05, then it means that the data is normally distributed. If it is less, then the data is not normally distributed. And you can see it by looking at the skewness of the plot. We may not go into that, but we can as well find out that. So let's start by checking for normality. Checking for normality. So checking for normality, we first visually see this, is there a normal distribution? So we do that by using a histogram. So we can just say hist by default, and we can say that we are plotting RCBD. This is our data example, and we are picking one variable, which is data. And then we just run that. So as you can see, it seems to be normal. The histogram from a look of things seems to be normal, but we are not sure. We need to run a Shapiro-Wilk test so that we can confirm the normality. So how do we do this? Let me copy this because we are just going to use it. We are just changing the function here. So we just run, we type Shapiro, just the way here is Shapiro.test, and we paste the same thing here. And then when we run this, it gives us an output here. And what we are interested in is this p-value. As you can see, it is above 0.05. And like I told you before, when it is above 0.05, then it means that our data is normally distributed, and therefore it calls for analysis of variance, which is a parametric method. So we are going to use that. There is another way you can do this. I think less R can do that. Library. Let's try library less R. You are used to this one. Less R has plot some very good histograms and violent plots. So let's use the plot command and we see what it is able to do. Plot data. Uh, map, and then we put data is equal to RCBD example. If you use this function, then we get something like this. This is a box plot, violin plot, all of them in that way. So it gives us these details, the minimum, the maximum, the median, the mean. So it is able to tell us something. As you can see also, it is not very different from what we can see. Most of the values are within between, they are 70 and 90. And that is the same thing it is showing here between 70 and 90. And as you can see from the mean, it is around 75 here, around here. This is our mean. So this one gives us some more information, or what we call exploratory kind of information before we do anything there. So with now that information, we can now run ANOVA. So running the ANOVA. So what does it take? There are two ways of doing this. One is by say running the model and then you take the ANOVA of the model. Another way is by just doing ANOVA directly. So let's do the quickest and the best way, which I think is the ANOVA. So I will just call it ANOVA. I will first store it in an object. And we use the AOV command. That is the what means analysis of variance. And then we shall say that now our dependent variable is data, and we use the tilde. That is a button above the escape, below the escape key on your keyboard. And then we shall say that plots, because plots is one of the things that one of our independent variable, and then insect side, comma, and then the data is equal to RCBD example. This is what we need to run ANOVA. So has really nothing has happened. Let's just print out the summary of ANOVA. This is what will give us what the real ANOVA is. So as you can see, it shows us that plots, the plot where you have put your seed or whatever, is having a significant influence on the yield. The same applies the insect side. Here we are talking about the seedling. Both of these two have an influence, significant influence on the number of seedlings. But then we need to know also sometimes to go a bit more than this and we ask which plot has the highest or which insecticide has the highest. Sometimes we do, you go ahead and you say post hoc analysis, and that way we can use like the 2K HSD, honesty significance difference. And like I've put it, it is as simple as that. You just write the word 2K, HSD, as you can see, just comes, and we are taking the 2K of ANOVA, just like that. And then it gives us this output. As you can see, it tells us the details. This is what sometimes we call the Take multiple comparison of means. And when you look at this, it's showing plot 1 and plot 2. Is there significance difference? Yes, you can see the P adjusted is below 0.02. Same applies plot 3 and plot 1. And then plot 2 and plot 1. Then plot 2 and plot 3, the same thing. Plot 4 and plot 2, the same thing, significant. But plot 4 and plot 3, there is no significance difference. That is for plots. It goes ahead and also compares the insecticide types. There is no significance difference between B and A. As you can see, the p-value is less than 0.5. Same applies to C and A, and the same applies to C and B. That is what Take multiple comparison of means does. It shows you which one is different from the other. So you can see it goes beyond the ANOVA and goes into the details within plots, which one is significant and which one is not. And also, that's not enough. We can just plot this, just like plotting these results, plotting the Take, the 2K, HSD. And it is as simple as just enclosing all this within the plot command, just by putting plot, open the parenthesis, just put that and run it. It plots something here. What you are seeing is for this. As you can see, when you say this, the lower part here is negative 11. This is the one, and negative 2 here. Then 17, CA, you see, it is at 17 here and 26 around here. And then 24 and 33. This is 24 here and 33 here. This is for insecticide. But there is another graph here for the plot. Here you may not see everything until I zoom. So when I zoom, you are able to see all these results plotted. The values, the lower and upper boundaries are plotted. So this is the way you can visualize the Take multiple comparison of means. And then you can now know where the problem is or where the variation comes from as far as the yield or your, for example, in this case, the seedling germination from these different seeds is coming from. Is it from the insecticide? Is it the effect of insecticide? Is it the effect of the plot? If yes, which plot and which insecticide? So, thank you. That's what we can do for now.